Hello class, this is Dr. Wessel, and this is a tutorial on static equilibrium where we have to be concerned with torque. I want to remind you before we begin that at any time you can pause the video to test yourself on either the vocabulary or even working out a problem, and then you can restart the video to see if you were correct. So let's begin. So what does static equilibrium mean? Hopefully you recall that it means that the acceleration of the object is equal to 0. And now that we have to be concerned about rotational motion, we have to think that the rotational acceleration is also equal to 0. So what does that mean? Well, it either means that the object is moving with a constant linear velocity and a constant angular velocity, and therefore not accelerating, or either of those could also be 0, or both could be 0. So most of the problems that we'll deal with at the beginning will be problems where the object is not moving at all and not even rotating. And so it still is a static equilibrium problem because in that case the forces all have to balance, or the net force has to be 0. Now, because we have to be concerned about two dimensions, we have to realize that the forces in the x direction have to be net 0, and the forces in the y direction have to be net 0. Okay. Now, also remember that when you have a static equilibrium problem, mathematically, it's a lot easier often to set these up as that the sum of the forces that go to the left have to balance the sum of the forces that are directed to the right. So that's sometimes an easier way to think about this. And naturally, then in the y direction, you can think of that the sum of the forces that go up have to balance the forces that go down. Okay, that's another way. Now, in terms of instead this rotational acceleration being 0, we have to worry about the torque. So that requires that the sum of the torques are 0, because a torque is what causes an inertial mass to accelerate rotationally. Now recall that in torque problems you can have a torque that is directed clockwise or counterclockwise. So in this case, if it's in static equilibrium, it's going to be useful for you to think of the clockwise oriented torques balancing the counterclockwise torques. Okay? And remember, clockwise goes like a clock in this direction, and counterclockwise goes in the opposite direction. So those have to be balanced. So you're probably wondering why it is I have this figure down here, and hopefully you've already guessed that it's a seesaw. It's also called a teeter-totter, and you find them at the playground where children play. And so I want you to imagine that naturally this thing can rotate, and as you can see it could rotate this way or this way. Okay. And we'll imagine a child that wants to ride on the teeter-totter, and so that child will make the child over here, and I'm just going to make a stick figure. Child. Okay. And the child's dad, Big Dad, twice the mass of that child, wants to ride with the child on the teeter-totter. So my question for you is, where does the Big Dad have to sit on the other side to balance the child in order to safely teeter-totter? Well, if you realize that the dad is twice the size, and you remember the formula for torque, let's put that down over here. Torque, right, is equal to R times F perpendicular, or torque is equal to R perpendicular times F. So this is really the equation that we need to worry about, because all of our forces will be perpendicular in this problem. So the force of the child is pushing down here. And the question is, so where's the dad going to sit? Naturally the dad, hopefully you realize, the dad has to be twice as close, because the dad's mass is twice as large. So if we write his force downward, 2 mg, and we compare it to the child's of mg, and we want the torque that they create, Let's make the torque of the child in the red going in this direction, and the torque of the father going in this direction, all about our pivot here at the center. Okay, if these are to balance, then it must be that the radial arm for the father compared to the radial arm for the child has to be twice. Because their product, right, the torque, which is the product of the radial arm length times the force that's directed perpendicular, and our forces are perpendicular. So the torque created by the child is 2r times mg, and the torque created by the father is r times 2mg, and so you can see that the torque in the clockwise direction is balanced by the torque in the counterclockwise direction. Now what about the forces in this problem? Are the forces balanced, and where are the forces? Well, let's see. Let's add the forces in a different color so that we can distinguish them. So the forces now, of course, and partly are already drawn here. We have the child going down here. We'll add it in light blue, and the father going down. So if there's two forces going down, and this is in static equilibrium, we need to have a force going up. Where do you suppose that is? It's at the fulcrum, naturally. And so the equation that you would use to relate the forces in this problem are really only Fy. And so the up force, which is the force here at the fulcrum, will have to balance the down forces, which is the total of the 2 mg and the 1 mg for the child. So that would be an equation we could write for them. Okay, so let's try a more challenging problem. Okay, in our first challenging problem, we have an arm, someone's arm, your arm, supported in a sling with the elbow at a right angle. So here's your arm, okay, and here is the sling supporting basically the arm. And let's add the information about the 40 degrees in here. All right. Now they ask us to consider the forearm and hand treated as a uniform mass, or as uniform with a mass. When they say something is uniform, that means you're going to treat it as a uniform geometric shape. So the forearm here is going to be of uniform shape, and it means that this mass should be taken at the center of the geometric object. So let's add that here right away, that the mg for our arm is going down. Okay, what else do they say? And they give us the length here of the arm, and they ask us to find the tension in the sling. So you always want to give a symbol to what you're being asked to solve for, and let's include it on our figure. So tension, and the tension is going this way in the sling. That's what we're asked to solve for. And we're also asked to solve for the components of the force exerted by the elbow. Okay, so here's the elbow. There must be forces exerted by the elbow. So we'll have to draw those in when we know more about them, and we'll have to calculate them. Okay, so first of all, why is this a static equilibrium problem? Well, nothing's moving, and they're talking about forces. And why is it a rotational equilibrium problem? Well, an elbow is a joint, and a joint can rotate. So you want to think about this problem as having a fulcrum here at the corner at the elbow. Okay? And also because this is a static equilibrium problem, to solve it, right away you might want to write down the three equations that we know apply. We know that the sum of the torques has to be 0. We know that the sum of the forces in the x direction has to be 0. And we know the sum of the forces in the y direction has to be 0. Now, whenever I see a problem with a pretty simple place to put a fulcrum, I usually go for solving the torque part first. So let's see what we can do to write equations. Any of those three places you could, in theory, start. But I like to start with the torque. So we have a fulcrum indicated. So now we have to think about what forces are making this thing not rotate clockwise and or or counterclockwise. So let's get a clockwise and a counterclockwise direction going here. So if you think about it, if our fulcrum is right here, okay, then this mass makes the, could make the arm want to rotate in this direction. So we're going to add, I like to add a little rotational, which way it's going to make it want to rotate arrow. So that would be for the mass of the arm. Now the tension is pulling in this other direction. So it must be making this want to rotate, or potentially exerting a torque in the counterclockwise direction. So we have a clockwise torque balanced by a counterclockwise torque. But we have to be careful because this tension is at an angle. And remember that our formula for torque, right, is the fact that the torque is equal to RF perpendicular. That's the simplest version of the formula, I think, to use here. So the perpendicular component of the tension that's making this want to rotate counterclockwise, potentially, is right here. And it's Ty. So Ty is really making or providing the component of the force that potentially is making this want to rotate in the counterclockwise direction. So what you have for the torque problem is the fact that the Ty, so let's write this actually in more detail. Let's write it like the clockwise torques have to balance the counterclockwise torques, so we're nice and organized about this. And the clockwise torques, well, it's force times the radial arm. So the clockwise torque is the red one, and that is M times G, and the radial arm, I'm just going to write the number in here, 0.15. Remember, it's half of that given 3 meters, right? And that has to balance, right, the torque, the blue torque, right, which is Ty times 3, basically. Okay? Recall, of course, right, so that when you go to substitute, so you get 0.15 mg is equal to T, now Ty is T sine of 40. All times 3. Now let's see what we have and what we don't have. Well, we have the mass, and we have, of course, gravity. We don't have T. We're asked to find that. We can do the sine of 40, and we can multiply by 3. So you can solve for T in this problem. So the tension turns out to be, if you were to solve it, 9.92 newtons. Okay? Now that's just for the torque part. Now what about the forces exerted by the elbow? Well, first of all, why would there be forces exerted by the elbow? Well, if you think about the forces balancing in the x direction, all right, over here, this T has a Tx. So let's add that in there. Let's add it in just simply black. So there's a Tx. Okay, Tx. Because that's the direction that the cable or the rope is going. Okay, so if there's a force going in this direction, there's a balancing force in this direction. So right away, hopefully you realize that there must be a force that's exerted here, and part of it, at least, is going in this direction. So let's call this f of x. So that actually is what this problem is asking. It's asking for the force exerted by the elbow, the components of the force. Now, as the question, is there an Fy? Well, there could be. So let's add that in here too. Right? We'll have to find that out from math, right? Because all the forces are going to balance. So let's see. Let's do the x forces first. So remember that when the sum of the forces in the x direction balance, it's like the left's balancing the right. So we have only this force directed towards the right and only this force directed towards the left. Those are the only left-right forces involved at all. So we can right away say that Tx is equal to Fx. And we can find Tx. Tx is T times the cosine of 40 degrees. That's fx. So we know t, right? So we can calculate fx. Now let's see if there's an fy. Oh, before we do that, let's write that value of fx that you would find if you did that. Fx turns out to be 7.60 newtons. Okay, good. Now what about Fy? Circle both of these. So the sum of the forces in the y direction, that means that the upwards forces have to balance the down force. And again, we don't have to worry about the r's for the balancing of forces equations. So to write the balancing of forces up and the down direction, we would say that Fy is an up force, and that it, together with Ty, which is also an up force, have to balance mg. Right? So this is the sum of the forces in the y direction has to be equal to 0. So what do we know here? Well, we don't know Fy, that's what we're looking for. But we can substitute for Ty, right? T times the sine of theta. We know those values. And we can set it equal to m and g, which we know. So we know everything here except for the unknown. So if you were to solve that out, you would find that Fy is equal to 6.38 newtons. So let's see if that makes sense. Well, it means that there is an upward force exerted by the elbow on the upper arm here, and there's an x-directed force exerted in that direction. So there must be some, basically, some force exerted by the elbow in that direction. So let's try another problem. Okay, in our last problem we have a person balancing on a ladder, and they give us where the ladder meets the wall up here, 3.8 meters, and they tell us where the person's weight is directed at a place 0.7 meters along the floor. So this is indeed a static equilibrium problem, and it also has a rotational feature to it. If you imagine a fulcrum in this position here, it's kind of like a rotational problem because you have a force here that makes you want to potentially rotate or slide, if you will, in that direction. And then you have a force exerted by the wall up here that makes you potentially want to rotate or keeps you from rotating in that direction. Okay? So that's the torque part of the problem. What other forces are involved? Well, the problem asks us to solve for the forces exerted by the floor on the ladder. So we have an upward directed normal force here. Let's call that F1. We have a frictional force here. We'll call that F2. And of course we have this force exerted, a normal force by the wall on the side, F3. So those are the forces that we're asked to solve for in this problem. So let's start by writing the three general equations and then try to decide which one is going to serve us the best. So the sum of the torques is equal to 0. The sum of the forces in the x direction is equal to 0. And the sum of the forces in the y direction is equal to 0. Okay, well, in the problem we are given the mass, so let's write that down up here. So the mass of the person is 85 kilograms. And then they gave us the dimensions there on the side, on the figure. And that's all they gave us. Okay, so let's try to figure out which of these three equations is going to be the most useful to use first. We have a pivot for the torque. You got a torque here, mg, and then, the distance is going to be messy. And then we get a torque up here, and that distance is going to be messy because neither of these forces are directed perpendicular to our lever arm. So I think we should come back to the torques. They're going to be complicated. What about forces in the x direction? Well, F2 has to balance F3, but we don't know either of those, so that's not a good place to start. Let's see if the y direction is any easier. F1 has to balance mg. Those are the only two up and down forces. So that's easy. We can do that. So let's write that equation first. So using the up balancing the down, we're going to say that F1 equals mg. Terrific. We know m, we know g. We can solve for F1. And F1 turns out to be 830 newtons. Easy. Great. Okay. Now, what else can we do? Well, let's see. Fx would probably be what I would want to go for next, but we don't know either F2 or F3, and those are the balancing forces. So I think that we're going to have to tackle the torque problem. Okay, so how do we tackle the torque problem? So with the torque problem, this is a funny one because the force is not directed at a right angle to our lever arm. Neither of these forces are directed at a right angle. So as soon as you see that that's the case, you have to worry about finding either the perpendicular component of the force, and they don't give us any angles, or using R perpendicular. And that's what this problem is about, finding R perpendicular. So remember that R perpendicular is the perpendicular distance from the extended force line to the center of rotation. So let's see if we can understand what that means. So here's our lever, and here's the force, okay, which is not at a right angle. It's not at a right angle. It's going down this way. So when you have to find R perpendicular, you want to extend that force. That's why I've added this line here, until you can draw a line that's perpendicular from the fulcrum. Here's the fulcrum. So it's this distance across here is actually R perpendicular for that clockwise directed torque. So that's R perpendicular. So actually for the clockwise directed torque, we have R perpendicular, which is 0.7 given in the figure, and we have mg. Now let's see if we have the counterclockwise torque. Again, it is not directed at a right angle with respect to the lever arm or the radial arm. And we don't have any angles given in the problem, so we have to look for R perpendicular. To find R perpendicular, what you should do is extend this force line. Now I'm extending it to the left because that's the distance where I would draw or think of this perpendicular. This is the R perpendicular distance, and that's given over here on the right hand side of the figure conveniently. So it turns out that in this problem, the two perpendicular distances that you need are given in the problem. And they were hard to find, I think, for a student. So how do we write the torque part of the problem? Let's write our overriding equation, which is the torque clockwise has to balance the torque counterclockwise. Now the torque clockwise is the red torque, so I'm going to write that one in red. And it's F times R perp. So it's M times G. Now R perpendicular here is 0.7. Now that has to balance the counterclockwise torque. Now the counterclockwise torque is F3 times its R perpendicular, which is 3.8. So as you can see, we can solve for F3. And if you were to solve for F3, you would find that F3 turns out to be 150 newtons. Okay, so our last problem is to solve for F2. So using the fact that the sum of the forces in the x direction are balanced, we know that F2 has to balance F3, and we know F3, so F2 also equals 150 newtons. So here's your three final answers. Okay, so let's quickly review what we learned in this problem. Okay, so it is a rotational static equilibrium problem. We put a pivot at the bottom because when the ladder slides, or because this mass is pushing down and the wall is pushing that way, it's like a rotational equilibrium problem, and you can solve it that way. The tricky part of the problem was the fact that the force was not perpendicular to the lever arm. So, and we weren't given any angles, so we couldn't find the perpendicular component of the force. So we had to extend the force line and then figure out what that distance from the pivot or the radial arm is along there to that extended force line. So in this figure, this was our perp for this force. Now this force is directed this way. It's also not at a right angle. So what we had to do to find the R perpendicular for that torque was extend this line. Since this is the center of our circle, it makes sense to extend it this way. Draw yourself this shortest distance here, and that turned out to be the R perpendicular for rotating in the counterclockwise direction. So those are pretty challenging. So I hope that you found the video helpful. I'm sorry it was kind of long, and I guess I look forward to seeing you in class soon. Thanks for listening.